So this is chapter 11, gases. So learning goal is to describe the kinetic molecular theory of gases and the properties of gases. All right, so before we get all crazed out because it says kinetic molecular theory of gases, and the properties of gases, we have to understand what kinetic means. Kinetic means movement, motion. So basically, how do gas molecules move back and forth as they bounce around in this crazy world we call, well, the world. All right, so solving equations, we'll go through that. That shouldn't be too big of a deal. Core chemistry skills using significant figures and calculations. I'm assuming that you guys have already gone over significant figures. And the fact is, you can only be as significant as your least significant figure. So if you have no decimal places, you cannot really come up with an answer without or with a decimal place, because you can only be significant as your least significant digits. Using conversion factors, we live in a crazy world where, especially in the United States, we like to mess with the standard system of measurement versus the metric system of measurement, as does the rest of the world. Real life example of that is when I I did evacuate an entire plant in Mexico as a young engineer because I did not take into account that their temperatures were in Celsius and not in Fahrenheit. So, go me. Molecular mass, talk about all that. All right. So, we're surrounded by gases. So, here's a couple examples of binary gases or binary molecules. Now, I don't know if he's talked about this, but hydrogen, nitrogen, oxygen, fluorine, chlorine, how they have H2, N2, O2, F2, Cl2. Those are molecules that don't like being out on their own. They need to become stable. And so to become stable in the world, they'll combine up together, or obviously with other elements, but they're naturally occurring as binary pairs, okay? Hence the word bi, or prefix bi. All right, some non-metal oxides, CO, CO2, carbon dioxide, NO, NO2, SO2, SO3, low molecular weight hydrocarbons, methane, so C, H4, propane, C3, H6, H8, sorry, I'm trying to do this in my head, and so on and so on and so on. Actually, the hydrocarbons are where most of your plastics are actually derived from, these base molecules. All right, so gas behavior. The behavior of gas is quite different from that of liquids and solids. Okay, we know that solid, definite volume, definite shape. Molecules are moving pretty slow. At a microscopic level, or atomic level, they're just kind of snailing it along. Liquids, defined volume, but not a defined shape. They'll take the shape of the container. So if we were to freeze the world and then pull out the water and then look at it, it would be the shape of all the recesses in the world. That's how the oceans get their shape. And then finally, gases are less dense than solids or liquids, and they're easy to compress. That's why we have compressed air and compressed nitrogen and compressed oxygen and all of these acetylene and things of that nature. They're easy to squeeze together because the molecules are just bouncing around. And as they bounce around, if you take a container, you can get them to confine in a smaller and smaller and smaller space, to the point where they'll if you take a highly compressed container and shake it, it sounds like a liquid, like there's something in there. But as soon as you were to open that container up, since those molecules are like hyperactive and they're just bouncing all around, they would actually it would just come out as a gas. So, kinetic molecular theory of gas states a gas consists of small particles, atoms or molecules, that move randomly with high velocities. The attractive forces between particles of a gas are usually very small. Okay, so what that means is, we already talked about the high velocity, that they're just banging around, just flying off the walls. And we can actually see this, and perhaps Lisa on Tuesday, the 21st, she'll have access to some liquid nitrogen, and she might be able to show this. But while they're at room temperature, gases that are at room temperature, those molecules are just bouncing everywhere. That's how a balloon inflates or your car tires inflate. But when we decrease temperature, the molecules are going to slow down, okay, because you're reducing the amount of energy given to them. So it's and we live in Ohio, so we know drastic changes in temperature. So we know going from very hot to very cold. And if you check your tire pressure on a 90-degree day, it might be at 40. Now all of a sudden, it's Ohio, temps drop 50 degrees, check it again, all of a sudden it's like 25. You're like, what's going on? Well, what's going on is the molecules are actually collapsing. They're slowing down, and that means they're not bouncing around with as much force, meaning it appears that, it is not as inflated, but it's really because there's not as much velocity on the molecules to keep that tire expanded. Okay, and then the attractive forces between the particles of gas are usually very small, meaning that they kind of want to stay away from each other. They really aren't like, hey, what's going on? Let's part. They just kind of they see each other and just bounce away. The actual volume occupied by the gas molecules is very small compared to the volume of gas it occupies. Now that's you read that and it reads like, what? The actual volume occupied by the gas molecules is very small compared to the volume the gas occupies. That means the amount of area or the amount of volume that is available, the space available. There's only 20 molecules for giant space in comparison, as where if it was a liquid, it would be 2,000 molecules for the same space. All right, gas particles are in constant motion, moving rapidly in straight paths until there's something that acts upon them. Then they are deflected and then bounce back and forth and back and forth and back and forth. Okay, much like if we were in a padded room, which some people think I belong in, and I were to bounce into one side of the wall. Well, what's going to happen? Well, physics says that, hey man, I'm going to go to a straight line, and so an equal or opposite force acts upon me. Well, that wall is going to be that force, so I'm going to then go backwards. The average kinetic energy of a gas molecule is proportional to the Kelvin temperature. Remember, 0 Kelvin is absolute 0. So in the realm of Kelvin, we don't reach the freezing point of water till we're at 273 Kelvin. All right, so the Kelvin scale. Remember, there's 3 scales of temperature we normally encounter, and that would be Kelvin, Celsius, and Fahrenheit. Okay, so that's that. So we see this when gas particles strike the wall of a container, they exert pressure, they exert force. There's like punching. Okay, if we heat the gas, the molecules are going to move faster and faster and faster, and they're going to strike with even more force. It's like me pulling my arm back and just kind of pushing it forward at a speed of 1 mile per hour. Now, if you think about professional boxers, they pull their arms back and exert a force at 20 miles an hour. Well, who's going to hit harder, me or the professional boxer? Well, obviously the professional boxer, because they have a lot more momentum behind that punch. So atmospheric pressure is the pressure exerted by a column of air from the top of the atmosphere to the surface of the earth. Okay, so it's about 1 atmosphere or a little less at sea level. Okay, so this is the pressure that's exerted on us every day, all day long. And this is what we see day in and day out. Okay, so, but pressure does change. If you guys have ever seen cooking instructions on a box of food, and it'll say at sea level, cook it this way. Well, at an elevation of 5,000 feet or above, you need to cook it this way. That has a direct relationship to the idea of atmospheric pressure, because the higher you go, the less the pressure is. So the volume of gas equals the size of the container in which the gas is placed in a container with a flexible volume. So meaning adding more particles increases the volume of particles, but it doesn't change the container size. lowering the temperature of the gas reduces the kinetic energy, decreasing the volume of the space they occupy because they're not bouncing as hard, meaning we can fit even more and more and more molecules in. So if I had a giant container of oxygen, okay, and O2, and I put it in a pressurized vessel at negative 100 degrees Celsius, all right, so the pressure will be, let's say 500 pounds, which it wouldn't be. I'm not doing the calculation, I'm just saying. Now, as soon as I bring that up to 0 Celsius, the pressure may be 5,000 pounds because the molecules have been warmed up, so they're moving at an ever faster speed. Temperature. The temperature of a gas is related to the kinetic energy of its particles, and it is measured in Kelvin. Well, we can measure it in Kelvin, or we can convert it to Celsius, or we can convert it to Fahrenheit. But standard scientific measure in chemistry is Kelvin. So, for example, a rigid container heating the gas will increase the energy of the molecules and therefore increase the pressure of the gas inside the container, just like I just said. So they're using the example of adding air to a bicycle tire. Higher pressure, blah, blah, blah. So usually the mass of a gas is measured in grams. In gas law calculations, we change the grams to moles because really, if you think about it, we can't go ahead and grab a spoonful of air and put it on a scale. So we will convert the grams to moles so we understand the actual mass, and there's a direct relationship, right? We've got 6.022 times 10 to the 23rd equals 1 mole of something, and then we can relate that directly back to the atomic number, do those calculations and figure out, okay, well, this is the atomic mass, and this is how many moles per gram, this is how many atoms, so we can do that calculation. So, properties that are described a gas: pressure, so the force exerted on a gas against the walls of a container. It can be in atmospheres, it can be in millimeters of mercury, or it can be in torr or Pascal. Okay, any one of those. I guess the English equivalent for us is normally atmospheres, but I know in the industry that I've dealt with, it's normally millimeters per grams of millimeters of mercury. Volume, space occupied by the gas, obviously. So that's a volume, liter, milliliter. We could say gallon if we wanted to. We could say a cubic yard. I mean, it's volume. 3 sides, length with height. Okay. Temperature, Celsius or Kelvin. But again, we can't use Fahrenheit. We'll just have to convert. And then the amount, the quantity of gas present in a container. So normally in grams, but for gases, we'll express it in moles because it is required. All right. So let's check how we learned. Okay, properties of gas described by each of the following. Increase of identify the property. Well, I would ask you this in class. So just think about these things. All right. Temperature, pressure, volume. Did you get it? Yeah. All right, great. So that is 11.1, and we'll go on to 11.2.